might have mentioned it. So for teachers. So, all right. So, chemical reactions. You know, a chemical reaction has occurred if you've got new substances, and we talked about how do you know new substances are formed. Well, sometimes it's a color. Okay, if you think back to your the copper lab we did, sometimes we are.
No, we did this one.
Did we do this one?
Yesterday, or whenever we were here last.
Oh, we're on this one. Okay. This other one's got chemical equations. Well.
Okay.
Sorry.
Yeah. Yeah. Okay.
I was looking at
It must be coming up. You're fine. So it's the whole. They're written chemical equations that represent the reactions are written from left to right. So we have reactants go to form products. Reaction arrow. Sometimes I think this reaction arrow, I think of time. This is kind of a little bit of a review. Go to form products. And basically, remember we said, and sometimes I'll put kind of a brick wall here, and basically what you begin with regard to atoms, and we're going to kind of do a little bit of this today, what you start with needs to be what you end with regard to atoms. And we kind of said on Wednesday, it's basically the nuclei of all atoms remain unchanged. So if you have, for instance, 3 sulfur atoms and 2 hydrogen atoms, you need to have 3 sulfur atoms and 2 hydrogen atoms over there. That's just it. So there are kind of this would be our equation. There are 2 types of equations. There's an equation that is unbalanced and an equation that is balanced. And it's just a fine detail. I wouldn't worry too much about it. The balanced, for sure, make sure, for instance, you have 3 and 2. Okay, that's what the balanced does. The unbalanced is not to be overlooked either. For instance, both types of equations that represent the reaction can tell you what is the physical phase of the reactants and what is the physical phase of the products. So in your copper lab, all of your little equations had this little thing next to the reactant or product. Of course, S is a solid, L is a liquid, AQ means it's dissolved in water running around, and G is a gas. So I really like chemical equations because they are like a shorthand, very concise. I'm not a wordy sort of person. You know, I am not a wordy person. So equations are like, oh yeah, they tell a lot. The other thing that an equation can do, and usually it's written over the time, over what we say the reaction arrow. Other things that they can do is tell the story, like, for instance, do you need any sort of heat? Okay. Okay, do you need to add a catalyst? Okay, and a lot of times, like I said, I'll be over the reaction arrow to tell you these things. Nice, concise. Okay. So I want to spend a little bit of time now talking about equations that are balanced, equations that have the same number of atoms on both sides of the reaction arrow. So these have done for us, and let's just kind of by inspection look what this means. The word stoichiometric coefficient, I know that's like a big, sometimes we call it stoichiometric coefficient. All it is a number that you put in front of the stuff that's reacting or being formed. A number that you put, a big number to the left to basically say how many of those units are in your reaction. So here we go. Here's the first one. Okay, so we have 2 reactants. We have P4 and Cl2, because then you find your reaction arrow, okay? And they're going to form what we say PCl3. So if we were to go ahead, and this is how this works, so we're going to do a few of these. I'm going to go ahead and put my brick wall here between my reactants and my products, and I'm going to go ahead and count P and Cl on both sides, P and Cl. So if I count P's, it looks like I have 4 over here because of that, and I have 2 over here because of that. Does that make sense? Then on the product side, looks like I only have 1 P in PCl3, and I've got 3 Cls. Right? So it's a great equation, but it's unbalanced at this point. So let's go ahead and see if now those boxes I revealed, okay, that, I'm going to put a squiggle underneath it. That actually, those are stoichiometric coefficients. Those are stoichiometric, it's a big word, stoichiometric coefficients. It just means it's a big number to the left that says how many of those units you have. So what's the stoichiometric coefficient in front of the P4?
0.
It's not 0. What's the what is, if we say H2O, how many oxygens are there?
2.
There are 2 hydrogens and
I mean 1 oxygen.
1 oxygen. Yep, exactly.
So 1 would go.
Yep, so it's an implied 1, exactly. The stoichiometric coefficient, if there isn't a number, is just 1. You got it. So now let's go ahead and let's do another balance. Here's my brick wall. I'll make it in purple this time. And I'm going to have to count phosphoruses and chlorines on both sides. Okay, P and Cl, P and Cl. And let's count again. So, let's go with the P's over on the reactant side. So it looks like I have still just 4 phosphoruses. By that. Now chlorines, this big number, this coefficient number, means that I have 6 Cl2s. So how many individual chlorines do I have? I have 6 pairs of them.
12.
I have 12. Yep, exactly. You buy that? Let's look at, that's where we're going to do some examples. We're going to do several examples, but that is exactly right. We have 6 Cl2s, so we have 12 individual chlorine atoms. Similarly, over here, I have 4 PCl3s. How many P's do I have?
4.
I have 4, yep. Very good. How many individual chlorines do I have?
12.
I have 12. What do you think?
Yeah.
I'm liking it. Here,
So they're balanced.
so they are balanced. Yep. Smiley faces all the way around. Okay, when that person went ahead and put a coefficient of 1 in front of the P4, a coefficient of 6 in front of the Cl2, and a coefficient of 4 in front of the PCl3, then on either side we have the same number of P's and Cl's, phosphoruses and chlorines. Let's look at the next one. Okay, so this is a combustion reaction where we're burning, anytime you see oxygen combining with basically something that has carbon, it's a burning. So actually, let's go ahead and check. What's our stoichiometric coefficient in front of the CH4? It is 1, that's right. What's the coefficient in front of the O2? It is 2, yep. The coefficient in front of the H2O? It's also 2, yep. Let's go ahead, and I think it's balanced, but let's go ahead and take a quick check. Here's my brick wall. I need to count carbons, hydrogens, and oxygens on both sides. Let's see, carbons on the reactant side, looks like I have 1. Hydrogens, I have 4. How many oxygens do I have over here on the reactant side? Fingers. It looks like 4, exactly. You got it. 4 oxygens. Let's look over here on the product side. Let's see, carbons. I'm thinking just 1 from right there. Hydrogens. I have to figure out the hydrogens from over here. So how many hydrogens do I have? I have 4, yep. Now oxygens, this is kind of fun. So oxygens, actually, I have to count the oxygens here and here. So how many oxygens do I have in 1 CO2? I have 2 oxygens. And then how many oxygens do I have over here in 2 H2Os? I have 2. Yep. So I'm thinking 2 plus 2, we got 4 oxygens. So this is where actually you kind of look and see, does it match? And yep, it matches. We good with that? Okay, and the last one, I'm going to have you fill in the coefficients, but I probably won't ever give you something this semester that looks like this, okay? Just because. But it would be balanced, and feel free to go ahead and check it on your own. Okay. All right. So actually now I have some kind of pictures to go along with what we just talked about. So this is one of the ones that we looked at, methane CH4 being burnt in the presence of oxygen to form carbon dioxide and water. That's the one you just balanced. And if we just actually go with coefficients of 1, so if we go with the 1 CH4 reacts with 1 O2 to form 1 CO2 and 1 H2O, you can tell it's not balanced. Okay, the little black balls there are carbon atoms, the little white balls are hydrogen atoms, and the little red balls are oxygen atoms. So it's just kind of a visual look at, it's not balanced. The carbon looks okay, doesn't it? The carbon between the two, I think that's what this little slide says. I was looking at this in my office. So well, there's a carbon, 1 carbon, you're like, cool. But there's like 2 oxygens, and I got 3 oxygens over there. So you're like, nah, that's not right. I got 4 hydrogens over there and 2 hydrogens over there. So this is the same reaction, just going ahead and going with those coefficients that we filled in a little bit ago. If instead of reacting with only 1 molecule of O2, if we up it to 2 molecules of O2, and we go ahead on the other side, on the product side, make 2 water molecules. Now, if you count the black balls, which are carbon, they're the same. If you count the white balls, which are hydrogen, they're the same. If you count the red balls, which are oxygen, they are also the same. Just kind of a visual look at what we talked about. So this whole idea of making sure you have this, what you begin with is what you end with. Okay? The only thing that passes is time. So what you start with is what you end with. That's basically kind of a theme of the universe, is stuff is conserved. Stuff doesn't just disappear. Stuff doesn't just appear. Okay? So matter is conserved. It's true, actually. You can morph. You can start with an atom, one type of element, and actually, it's like alchemy. It's the atom morphs into another element, but that's and some energy is released. Okay, and that's not what we're talking about. That's nuclear changes. So let's see how we can balance some equations. There's another way to balance equations, but the best way probably for us is called trial and error. And I kind of kid students, if you're used to using a pen, this is where I would break out your pencil. Because what you're going to see basically is when you start kind of coming up with the 1 or the 2 or the 3 or the 4 to kind of make it balanced, sometimes you're going to actually be changing what you wrote down. That's why it's kind of trial and error and use a pencil. First off, you cannot change any of the subscripts. Okay, do not change the subscripts when you're doing this. Do not change the subscripts. Like for instance, in the previous example, we actually, one of the product was H2O, okay? We couldn't clean things up by making it H2O2. We could not do that. We could not change the subscript from 1 to a 2. It's tempting, okay? Okay? But what you can change are the stoichiometric coefficients. So sometimes I actually, when I do my answer keys, I will, I'll say like if you have 2 reactants, if you have, for instance, X reacting with Y to form Z, okay, Sometimes actually you'll see me put a little squiggly mark here, and that little squiggly mark is where I can put a stoichiometric coefficient. I can even put the stoichiometric coefficient of 1 if I want. If I leave it blank, it is 1. Okay, so you can do that. The other thing, and we actually saw an example of this, for instance, when we ended up with, was it 4 molecules of PCl3, okay, or 3 molecules of 4, I think that was, okay, recognize that this 4 applies to both the phosphorus and the chlorine, okay, that's all that's saying.
It's just the numbers added together. Like
They're
the that would be after them, like the P would have 1, then the Cl is 3, so you just add those together for the front numbers.
I think so. I kind of think of it as multiplying. All I meant like is if you break this out, the P's, you have 4 P's, and how many chlorines do you have?
12.
Yeah.
12. But I'm talking about to get the front number. The first big
Oh yeah, we're getting to that. How do you get the first big number? Yep. Yep. So she's like, she's saying, you know, how do you know to put a 4 there? And that's what we're coming up on. Okay. Coming up. All right, so we're going to do an example. This is much more the example than kind of earlier this morning I had like 3 equations in the back. That last one had something a lot really complicated. This actually is I don't think, too bad. So yeah, this is what Grace was asking. How do we, I'm going to go ahead and put squiggle marks here. How do we come up with those big numbers? And that's exactly what we're going to do right now. So I'm going to go ahead and put my brick wall. And there's different ways to do it. Some students don't need the tally sort of system. I'm going to kind of show you the tally. So it's just like I was doing before. So the tally starts like this. So I need to have irons and hydrogens. So I need Fe's, H's, and O's over here. And I need to have Fe, H's, and O's over here. And what I start out with is to go ahead and just put what they are with just ones there. So if I just go with ones, what they are just right now. So of course Fe's I only have 1. H's I have 2. Oxygens I have 1 on the reactant side. And on the other side, the product side, it looks like I have 3 Fe's. I have 2 H's. And I have 4 O's. Look okay? So it's really a back and forth. You know, we do a lot of things in chemistry or all sorts of problems that are just one way. This is actually kind of back and forth. So my hint usually is to, and I think I have on the next slide, if you see something up here that looks kind of simple, like the Fe looks kind of simple, I will leave that one till last. I will leave this till last. Okay? And I'll work on something that looks a little more complicated. Like, for instance, let's just fix our oxygens. Let's fix our O's. Right? So to fix our O's, we recognize that I have 4 over here, okay, and I only have 1 here. So to get 4 on the left, or the reactant side, how would I do that?
Separate the H2O.
I'm going to leave the H2O intact. And what number can I put right here where the squiggle is to get 4 oxygens?
4.
I can put a 4 here. Yep. If I put a 4 up there, does that give me 4 oxygens? Yep.
But wouldn't that give you 8 hydrogens?
Right, and that's why we're kind of, it's like a back and forth. You have to, we're not done yet.
Oh.
Yep. Heather's like, well, that'll mess up something else. And it usually does. Exactly. Yep. So I put a 4 there, and then we need to update. So, okay. So here are some updated values. When I put the 4 there, now my hydrogens are 8, right? So I'm going to find my hydrogen. I'm going to cross out the 2 and update it to an 8. Okay. So when I put a 4 there, that actually fixed my oxygens. So now I have 4 oxygens on both sides. I will warn you that sometimes you get down the road working these, balancing them, and then eventually your oxygens will be screwed up. So it's kind of like I said, it's kind of like rounding up cats. Okay. So for now, oxygens look good. Let's fix our hydrogens. So we have 8 hydrogens over here on the left, but we only have 2 hydrogens on the right. How can we get 8 hydrogens here? Mm-hmm. Put a 4 in front of the H2, exactly. 4 over here. So now we need to just update our H's. So how many H's do we have? How many? 8, yes. I think I said 3. I was like, no, 8. Perfect. So instead of 2, now we have 8. Okay, now again, sometimes you get down the road and it gets messed up, but so it looks like the only thing we have left are our irons. So I have 3 over here on the right, 3 on the byproduct side, but I only have 1 over here, so how can I get up this from a 1 to 3? By putting a 3 in front of the FE. So it's kind of like you change the coefficient and then you update your tally. So if we update our tally, so now of course instead of 1, now we do have 3 FEs. Okay, so let's kind of compare across the board. It's looking like our FEs are the same, our hydrogens are the same, our H's, and our O's are the same. That's it. Like I said, it's kind of back and forth.
With our homework that we're, or most likely homework with this, will it make a difference if we put a 1 instead of leaving it blank, or does it matter?
It won't make a difference if you put a 1.
I'm asking if it matters, like if it matters to you.
No, it doesn't matter to me. In fact, she's asking about the 1 in front of things. If I was kind of new to chemistry, I'd probably put a 1. And that's kind of the same thing when you're making your compound formulas. I'd probably put a little 1 subscript there. Yep, nope. I know a few slides ago it said a 1 is not usually there, but I would probably put it there. Any questions? They're kind of fun. And I might put out a tweet for those of you who follow me on Twitter. There's a website out there online that actually you can, if you get stuck on balancing an equation, all you got to do is put in the unbalanced equation and it will tell you what it is. So you're like, oh really? That's kind of, so every once in a while I'll get stuck. Any questions? So the last slide is a busy slide, but I do want to talk about this one last thing associated with chemical reactions. Just touch on it, okay? So chemical reactions are a funny thing in that, well, we all know that things can go boom, right? Things can go blow up, okay? And those would be what we call exothermic reactions, okay? Actually, sometimes that's liberating a lot of energy. Sometimes chemical reactions actually require energy, okay? So exothermic reactions, things that go boom, not necessarily, but things that actually release energy as they do their thing, okay, as the reactants go to form products, okay? They release their energy into the surroundings. And so this actually is kind of a picture of when we have a chemical reaction. Bless you. The chemical reaction is occurring in the beaker. That's actually where the chemical reaction is we call it the system, okay? The outside of the chemical reaction, which could be outside of the beaker, could be outside of wherever the chemical reaction is occurring, we call that the surroundings, okay? So kind of back to something that's explosive. It's basically transferring energy from the system to the surroundings. That's why you see kind of a little arrow going out like that, Okay, so I like this picture. Exothermic, though. Exothermic is the term I want you to kind of get here. Exothermic, exciting, yep. Basically, it is releasing energy to the environment or the surroundings. So this over here actually is a type of energy curve. So let's kind of see what it looks. It's almost three-dimensional. Can you see the 3D in it? It is looking at the combustion of the CH4 plus the O2, the burning of methane. Actually, that's what the little chemical reaction is. The way you read this, I guess we call it more of an energy diagram. The way you read this energy diagram is along the x-axis is time. Okay, along the x-axis is time. Along the y-axis is energy. Okay, so this is time increasing, and this is energy. So it's kind of cool because, again, these energy diagrams are nice and concise. They tell a nice little story. Notice that it is showing you reactants over here and products over here. That's exactly what we've been talking about. It's an energy diagram. Reactants go to form products over time. Now, the other thing this is showing you is that for an exothermic reaction, notice it starts with this much energy and it ends with this much energy. It starts with a lot of energy and it ends with less energy. It starts with a lot of energy, ends with less energy. And that energy needed to go somewhere, it went to the surroundings. It's an exothermic reaction. That's it. Now, the other thing I'll explain is the little hump. You see the EA next to that? Actually, that little hump is activation energy. So, this little hump, this little light of mine. I mean, chemical reactions are all around us, and we tend to, obviously, take them for granted, but we tend to take them for granted. In order for a chemical reaction to occur, actually, it needs to overcome what we call an activation energy barrier. So there you go. So exothermic. Now the other one is a little bit, well, first off, before I go, can you see where if my hands were around this Erlenmeyer flask, they get warm, right? Okay. All right, keep that in mind. The other type of reaction, kind of the yang to that yang, yin and yang, okay, would be this sort of chemical reaction. That is what we call endothermic. And so for an endothermic reaction, if you have your hands around an endothermic reaction, this is what it looks like. This little Erlenmeyer flask down here. Okay. For an endothermic reaction to what we say proceed, or for endothermic reaction for the reactants to go ahead and form products, they need energy. They're like the wraith. Okay? They need energy. So actually, can you see where if I had my hands around this, and I've got some thermal energy in my hands, think it would get cold? It does. This phenomenon of an endothermic process or an endothermic reaction, it makes a great cold pack. You know those kind of cold packs you take on the go? All you got to do is have something that's endothermic and So here's the energy diagram for an endothermic chemical reaction. Okay, so if you look, kind of compare the two, to me, one of the big things right off the bat is kind of, you start with this much energy, okay, and this is the system. This is inside the Erlenmeyer flask, and you end with this much energy. Okay, so you start with this energy and you end with this much energy. You have more energy. Where'd you get it from? My hands, if I'm holding you, right? Okay, that's really how that works. Endothermic reaction. Okay, but there is an activation energy for both types of exothermic and endothermic chemical reactions. All right. Does anybody have, you do have your book. I want to, so go ahead and jot these down. These will be due on Monday. But before I turn you loose, I do want to, can I look at your, thank you. I want to double check if all of these chemical reactions look like they be, you could balance them. So, page 392, exercise number 2. Let's see. Okay, I'll write it up here, but we're gonna make, for that first one, exercise number 2, we're gonna make letter D optional, because of those, I think that one looks the worst.
Do you get extra credit if we do it?
You, oh, I don't have a pot of extra credit points. Yeah, we could do that.
On our test. We could
Not
get
on your
extra
test. It will go for like assignment points, extra credit. I like that. So for number 2, 2D is worth extra credit.
I'm not even gonna put optional in.
Oh, yes, the pot of extra credit points. What's that?
I'm not gonna put optional in, because otherwise I won't do it.
All right. That's all I have today. I think we should quit. Happy Friday. And enjoy your cupcakes.
Oh, I will.
Thanks, Gracie. Grace.